Our next group is SAIL Engineering, which is an acronym, think of all their first names. And they were also working in Panama with the same organization, Footprint Possibilities. Their site was closer to Panama City, so a little more of a kind of suburban setting. And they have another water supply project to tell you about.
Good morning, we're SAIL Engineering. My name is Isabel Manson, Skylar Kruger, Allison Fenton, Will Sparks. And we're here to present our senior design project, which was extending a municipal water supply to Macomber, Arriba, Panama City, Panama. Oh, and our project was in partnership with Rick Montanari of Footprint Possibilities. Today, we'll be describing the scope of our project and going over the project constraints and assumptions that we had to make. We will present our EPA net model and additional component designs. We'll go over our construction schedule and cost estimates and conclude our presentation with some recommendations for the future.
So first off, just to get you familiar with the geography of the site, the first image on the left, it just shows you where Panama City is in relation to the country of Panama. And then the image on the right shows how Macombo Arriba is 25 kilometers approximately north of Panama City. Macombo Arriba is a peri-urban community, like Dr. Watkins said. So our team was tasked with designing a water distribution system. We are building off of a previous semester's project, previous senior design project, but the main difference between our two projects is the connection point for the municipal water source. Our project was located in Villa Garcia. That's where we tied in. That's 3 kilometers north of Macombo Arriba. And then their connection point was 2 kilometers east of Macombo Arriba. And then those are shown with the 2 circles right up top there. As you can see, Macombo Arriba itself was just divided into 4 sectors. Those were merely for design purposes, just so that we could adequately distribute pressurized water to each system, each area. Here's a quick summary of the phase 1 design. Their entire system was gravity fed. This was due to their higher elevation as a starting point, as their connection point. They estimated 3 months for construction, and then they had a total cost estimate of $600,000. That's slightly more than our cost estimate, and that's mainly due to storage tank coverage and more tank covers, which added to the cost of theirs compared to ours.
And some of the assumptions that we had to make while designing our pump station included the fact that most of the pipes will be implemented underground, excluding ravines, which will require suspension bridges. The above ground pipes will be covered in concrete, with the exception of suspension bridges. And we are assuming that all the locations mapped out in our model are community or residential areas. In terms of population growth, we're assuming an annual growth rate of 3% over the design's 15-year lifespan. And so this means we're modeling the system for 2,000 residents in total. For each household, a flow of 200 liters a day will be delivered, and this was recommended to us by Mr. Montanari, excuse me. And our design assumes that peak flows will be occurring at 8 a.m. and 5 p.m., and the flow pattern for the community is modeled in this figure. Our project's design constraints included the fact that there was a significant change in elevation across the community. This change was about 130 meters over a distance of 2 kilometers. We were also tasked with supplying the entire community of Macombo Arriba with water through one sector of the community, and that was sector 3. And we needed to ensure a minimum pressure of 10 PSI at each household without ever exceeding 50 PSI. And this means that we had to be intentional with our placement of storage tanks and pressure valves.
So our proposed design is based on it utilizes a commercial grade pump, and we have a base demand of that 35 liters per minute, which is supplying 2,000 residents with 25 liters per day per person. And with that base demand, we found this small pump that actually has a head of 105 meters, which is not exactly what we were shooting for with the 130 meter range in elevation, but it was close. And a similar pump with a similar pump curve, maybe with more pressure, with more power, would utilize this system very similarly. So going into our EPA net models, we actually modeled two different EPA net models. a supply system and an emptying stage. Our supply system starts with our pump house near the connection point in Villa Gracia with that that initial pressure of 10 PSI from the connection point had us have to move our pump station from up to the connection point, and initially it was going to be entered into sector 3. Up here you can see, there we are, up here you can see a pressure valve, brake pressure valve actually, which is where we wanted our pump station or our pump house, but we did not have enough pressure for the water to make it down this road. And what it does is it fills into these 4 different tanks, storage tank locations. And those 2 storage tank locations are placed about the highest elevation within each sector. And they are a single storage tank at each location except for the first one, which is sector 3. That's actually 6 storage tanks, and it holds a emergency days worth of water, emergency supply, days worth of emergency supply water, excuse me. So that's 8,000 liters each tank, and that's 6 tanks, 48,000 liters at the emergency supplies area. And it takes a full 23 hours for all of our tanks to fill to the peak. And that mostly is because of sector 4, which is our highest tank up near the top. It takes the longest there to fill. Okay. So our second model is very similar. It's that second stage piping where our tanks will go from, our piping will go from our tanks to our houses. And you can see a lot of green and yellow on the screen. That's showing positive pressure of 10 to 50 PSI, which is necessary for our households to not break their valves. So this part of the system is gravity fed. It's not actually using the pump at all. So from that connection point mentioned earlier, you can still see a brake pressure valve. We actually don't need that valve or the system piping up towards the pump location at all. It's just here in the model for a similar comparison. And we have 2 brake pressures valves in this half of the system, in between sector 3 and sector 2, and then in between sector 2 and sector 1. And that just solidifies that there's no backflow in the water, and the actual tanks are filtering into the houses within their sectors.
So our team was also tasked with designing our pump station. This consists of a structure to house our pumps in. The first image here on the left, you can see the outside view of our pump house with the door. It's made out of standard concrete blocks and contains some fluted ventilation block 3 rows down to allow for ventilation inside of the pump house. Obviously, Panama is a more warm, humid climate, so this allows anyone working inside of the pump house doing maintenance to live in comfortable conditions inside of there when they're working. We also have a heavy steel door with a deadbolt outside of our pump house. Footprint Possibilities expressed concern with security on this pump house. They didn't want it to be tampered with or damaged. So we've chosen to address this in a couple different ways, one of them being that heavy steel door with the lock. The middle image, you can see a little bit of the inside of our pump house. So it contains our pump and all of the electrical components necessary to run it. And then the last image of the entire pump station is our pump house sitting on a concrete slab surrounded by an 8-foot fence. That fence contains 3 rows of barbed wire on top and a locked gate. So those combined with that heavy steel door are kind of our security measures for ensuring our pump house is able to run for its entire lifespan. And we were also asked to design shade covers to protect our storage tanks from sunlight, which would heat the water, which is meant to be used for washing and drinking. Also, if the tanks were to be heated, the chlorine being used to disinfect the water could be evaporated. So it's protecting it from that as well. One large shade cover was designed for a tank farm of 6 tanks, and 3 smaller shade covers of equal size were designed for brake pressure tanks. And the general characteristics of the shade covers include a slope roof made up of 14 gauge galvanized steel and C-channel, which is suited to withstand rain and moisture.
Next up, we have our suspension bridges. Like we mentioned earlier, there's a lot of change in elevation throughout the community. And in order to help mitigate some of that and the pressure changes that would happen with those elevation changes, we might implement some suspension bridges. The design includes a steel cable being anchored at the 2 embankments. Steel cable is then supported with PVC rings, as shown in the figure, and then the pipe that will carry the water is run through those rings. This design is frequently used in Panama, and so that's where this image came from. Our pipe will be painted to protect it from UV degradation and for better visibility. 2 anchoring systems are possible for this design. One uses tree trunks and another uses a concrete block with eye bolts. The tree trunk is preferred method just because it would eliminate a lot of the cost of not having to create a concrete abutments. And yeah.
And this is our bill of materials. It was created for our design, and it includes an itemized list of all the materials required and their costs. The quantities listed for each of the items take into account a margin of 10% in order to ensure adequate supply of all of our components. And the bill of materials was organized into 8 separate divisions to make it easy to refer back to. Those divisions include the materials needed for the running pipe, water access, shade covers, suspension bridges, the pump house and the pump, and the equipment and labor needed for construction and maintenance.
So our cost estimate, we mostly utilized RS Means and a couple other trusted sources, and we actually got to a $300,000 estimate, which was half of the phase 1's design, which mostly is less than because of our minimum tanks and tank covers compared to phase 1's design. So our design is about 1/3 in our shade structures, about 1/3 in our running pipe, and only about 12% we are estimating to be our labor.
Here's a summary of our tasks for our construction schedule. We estimate about 6 months for the entire construction of the project. We have a start date beginning in January of 2023 and finishing up by the end of June of 2023. This will take place during Panama's dry season, which is preferred, which is January through May. A couple assumptions we made for this is that we'll only have access to 1 group of workers for it. Our cost estimate includes 1 supervisor and 5 laborers for this group. It's important that we only have that 1 group because then only 1 task can be completed at each time. This means that each task is a critical task, and if that task is delayed, then the entire project will be delayed. Yeah.
So in conclusion, access to clean running water is often thought of as a human right. This will definitely improve the quality of life for the people in Mocambo Arriba if the system were to be implemented. The community would experience many benefits, including social, economic, and environmental. So they would experience improvements to their economy as it would become a more desirable place to live. Community cohesion would increase as the community would be responsible for maintaining the system in the future, and it'd be working towards the goal of environmental justice, so giving everyone everywhere access to clean running water. Our system is a 2-part design that has a filling stage and an emptying stage, and our design is going to be reviewed by Footprint Possibilities along with the National Assembly of Panama, which is a legislative body in Panama, and they'll be looking into it for implementation. Our recommendations include exploring a road leading from Via Gracia down to Sector 4 rather than the road that we're utilizing into Sector 3. All of the land that we're planning to build on is known as public access land, but the road leading into Sector 4 we believe to be private land, but this has the potential to shorten that filling stage for our tanks. So this is something they could investigate if they were looking to supply a higher demand of water. They should verify these locations in the field and ensure all the land actually is public before beginning construction. We created an operations and maintenance manual for the community to use to install this system and maintain it for its entire lifespan of 15 to 20 years. And finally, we created a community health survey so we can monitor the impacts of this project if it were to be implemented in the future. Finally, our group would like to thank Dr. Watkins and Footprint Possibilities for collaborating with us on this project.
Any questions?
So you mentioned all the survey. Would you also like survey questions to mitigate any assumptions made for like, great. That should be a good presentation.
Oh, so using our survey to monitor the assumptions we made? Yeah, we could potentially do that. Right now, the survey consists of a lot of like what symptoms are you having and how has this impacted your life? And it is more about the health of the community members, but that could be utilized to maybe monitor if the project is actually fulfilling the needs of the community and maybe making modifications. If yes, they are census data assumption was incorrect, we could potentially up the demand for the project or something like that.
Yeah, it's a good idea.
So the suspension support system for the bike, second time I saw that. It's before. There's some things there that are a little disconcerting, like with plastic rings and pieces of pipe that are just to support it. I noticed it, when you mentioned concern about UV light deterioration. Just wondering why you didn't consider things like steel bands to compare strength. And then, if I understood correctly, the ends would anchor with a tree or?
So that was the first option, design option, and the other was a concrete abutment with a eye bolt connection for the steel tie through the steel cable.
Yeah, so I don't know if you know, like, the type of trees and how long they live there, you know? It's a little different than here.
Yeah, we didn't talk with our sponsor much about that, but like the other team also used, it's a design that's frequently used in that area just for cost reasons. And so we just adopted it for our design.
And it is difficult because we really don't have any concept of what the terrain looks like around there, apart from the elevation changes and the placement of the residential homes. So it definitely was a challenge for us.
So this was a question that another team had. It got me thinking, this is very hilly. And so are there concerns about having like inequitable supply, right? So some homes have good pressure, some homes not so good pressure. Any thoughts on that? Like what might be done to try to ensure use this term more equity across the system?
Well, actually, our system is supplying our homes with adequate pressure for a full day's worth of supply after that initial filling stage. We do recommend looking into that road going into sector 4 just to make that a little shorter. It might help minimize pressure during the filling stage, but we're using Schedule 40 PVC piping. We're not worried about the high pressure during the filling stage.
Another option that our sponsor talked about was just creating a community fountain where all the people could go and collect their water from instead of having it be delivered to their households.
So it seems like a lot of the material is steel or concrete. Are there any alternatives to those high CO2 demanding materials?
There probably is. A lot of our designs were based off of research papers that Mr. Montanari provided us. For example, we based all of our shade cover designs off of a proposed design that was designed by a team in UC Berkeley. And we were asked to base our designs off of that, and all of those designs were using 14 gauge corrugated steel. So, but there probably are alternatives.
The other team designed with wood first. Okay, sorry, I'm confusing it. Yeah, they were specifically asked not to design a wooden structure because of the termites. Sorry.
We did have a little bit of concern with safety about, especially with our pump station. So we did use a lot of concrete and steel for that for safety reasons.
Any other questions for this group? Thank you. Did I conclude this session? Thanks to everyone who attended, and hope to see you at the reception this afternoon. 4 o'clock up in the floor. as you mentioned, there are talks continuing, other things like now 6:41, 6:42.
Do you want me to stop the Zoom recording?
Yeah.
Stop it, sorry.
Yeah, good job.
Thank you.